Have you ever felt a tiny shock when you touch a doorknob on a dry day, or seen your hair stand on end after taking off a woolly hat? These little moments are our everyday encounters with a fundamental force of nature, electrostatics. It's all about charges that aren't moving, charges that are static. Electrostatics deals with the interactions between electrically charged particles. Think of it as the study of electricity at rest. Every single atom contains charges, protons with a positive charge, and electrons with a negative charge. Usually these charges are balanced, making an object neutral. But sometimes, electrons can be rubbed off one object and onto another, creating an imbalance. This imbalance of charge is what we commonly call static electricity. When you rub a balloon on your jumper, electrons jump from the jumper to the balloon, creating a force between them. This force can make the balloon stick to a wall, or make your hair stand on end. Electrostatics isn't just about minor shocks or amusing hair-raising moments, it's about a fundamental interaction that governs how matter behaves. Understanding these static forces was one of the first major steps into the world of electricity. And at the core of this understanding lies a beautifully simple yet incredibly powerful law. How do we measure these mysterious pushes and pulls between charged objects? Enter Charles-Augustin de Coulomb. Through delicate experiments, Coulomb discovered a fundamental principle governing the force between two stationary electrically charged particles. This principle is known as Coulomb's law. It states that the force between two-point charges is directly proportional to the product of the magnitudes of the charges and inversely proportional to the square of the distance between them. The formula is F equals K times the absolute value of Q1 times Q2 divided by R squared. F represents the electrostatic force, Q1 and Q2 are the charges, R is the distance between them, and K is the Coulomb constant. This law allows us to calculate the force and understand the nature of electric interactions. If you increase the amount of charge, the force gets stronger. If you move the objects further apart, the force gets weaker. Coulomb's law is a cornerstone of physics, providing a mathematical relationship for something invisible. It's a beautiful piece of scientific detective work. Let's look more closely at K in Coulomb's formula. This K is known as the Coulomb constant, approximately 8.987 times 10 to the 9th Newton meters squared per Coulomb squared. It acts as a proportionality constant, scaling the relationship between the charges and the distance to give us the force in standard units. Without K, the formula would only tell us that the force is proportional to the charges and inversely proportional to the square of the distance. The value of K is determined experimentally and reflects the strength of the electrostatic force in the universe. Interestingly, K is related to the permittivity of free space, written as epsilon naught. The relationship is K equals 1 over 4 pi epsilon naught. The permittivity of free space measures how well an electric field can permeate a vacuum. So, K isn't just an arbitrary number, it's deeply connected to the electrical properties of the vacuum itself. The significance of this constant is immense, appearing throughout the study of electromagnetism. It ensures that our calculations of electric forces are accurate and reliable. The Coulomb constant K is a key that unlocks our ability to quantitatively understand and manipulate electric forces. One fascinating aspect of the electrostatic force is that it can be either attractive or repulsive. Unlike gravity, which always pulls things together, electric charges can push each other away or pull each other closer. The basic rule is simple, like charges repel and opposite charges attract. If two objects have a positive charge, they will push each other apart. If one object has a positive charge and the other a negative charge, they will pull towards each other. This is the fundamental choreography of the electric world. When you rub a balloon on your hair, electrons move from your hair to the balloon, causing your hair to stand on end and the balloon to stick to a wall. Coulomb's law gives us the magnitude of this force. The direction, whether it's a push or a pull, comes from knowing the signs of the charges. This simple interplay of signs and magnitudes governs the electrical interactions happening all around us. It's incredibly powerful. The idea of forces acting at a distance can be tricky to grasp. To help us build an intuition for these invisible pushes and pulls, analogies can be incredibly useful. Perhaps the most common analogy is that of magnets. Magnets have a north pole and a south pole. Two north poles will repel each other and two south poles will also repel each other. but a north pole and a south pole will attract. This is very similar to electric charges, like repels and opposites attract. Another way to think about it is to imagine invisible strings. When two opposite charges attract, it's as if there's an invisible elastic string pulling them together. When two like charges repel, it's like they are both pushing on the ends of an invisible compressed spring. We can also draw a parallel with gravity. Gravity pulls masses together across vast distances, similar to how Coulomb's law describes electric forces. However, gravity only attracts, whereas electric forces can attract or repel, allowing for a richer set of interactions. Coulomb's law is a beautifully concise equation, but let's unpack what it tells us about the key ingredients that determine the strength of the electrostatic force. The first crucial components are the charges themselves, Q1 and Q2. These symbols represent the magnitude of electric charge on each of the two interacting objects. Charge is a fundamental property of matter, measured in units called coulombs. The law tells us that the force F is directly proportional to the product of these two charges. If you increase the amount of charge on one object, the force between them will increase proportionally. Now let's consider the R in the formula. This R represents the distance between the centers of the two charges. The force is inversely proportional to the square of this distance, known as an inverse square law. If you double the distance R, the force becomes 1/4 as strong. This inverse square relationship means that electrostatic forces are very strong when charges are close together, but diminish significantly as the charges move further apart. Understanding how both the magnitude of the charges and the square of the distance contribute to the final force is key to appreciating Coulomb's law. The final piece of the puzzle in Coulomb's law is the Coulomb constant K. Its value ensures that when you plug in your charge values in coulombs and your distance in meters, you get a force in newtons. It's the conversion factor that makes the equation work in practical terms. Let's imagine some simple scenarios to see how changes in charge and distance affect the force. Suppose we have two small objects, each with a positive charge of +1 Coulomb, and they are 1 meter apart. The force of repulsion between them would be nearly 9 billion newtons. If we double one of the charges, the force doubles. If we double the distance between them, the force becomes 1/4 of what it was. These conceptual calculations help us build an intuition for Coulomb's law. Knowing that doubling a charge doubles the force, or doubling the distance quarters the force, provides a powerful mental toolkit for predicting how charged objects will interact. It allows us to reason about the behavior of electrical systems. And it all stems from that elegant formula Coulomb gifted us. Coulomb's law isn't just an abstract equation, its consequences are all around us. From static cling to the structure of matter, Coulomb's forces are constantly at work. Consider static cling. When different fabrics rub together in a dryer, electrons can be transferred from one material to another. One piece of clothing might end up with a net positive charge, and another with a net negative charge. These oppositely charged items will attract each other. Think about photocopiers and laser printers. A photocopier uses light to create a charged pattern on a drum, attracting oppositely charged toner particles. Even the stability of atoms themselves is a testament to Coulomb's law. The attractive Coulomb force between the positive nucleus and the negative electrons holds the atom together. The very fact that matter is stable is due to the electrostatic attraction described by Coulomb's law. Coulomb's law is incredibly powerful but has its limitations. It applies best to point charges or spherically symmetric charge distributions. For more complex shapes, calculations can become more involved. Coulomb's law describes electrostatic forces for charges at rest. When charges move rapidly, they create magnetic fields entering the realm of electromagnetism. At very small distances, quantum mechanics comes into play. Despite these limitations, Coulomb's law was a monumental step in understanding the electrical nature of the universe. It laid the groundwork for much of the physics that followed, encouraging us to keep exploring the intricate workings of nature.